Next, let's take a system of equations and write it as a k-flat. This is exercise 2.5.37. Solve the system of equations, write the solution set as a k-flat. I went ahead and wrote out for the system of equations, the augmented matrix. We'll let Wolfram alpha do the row reduction, and it produces this. There's your reduced row echelon form. There's a pivot. There's a pivot. There's a pivot-free column. So we're dealing with a system of equations with one free variable. When we convert this into k-flats, that one free variable will correspond to the parameter k, and we'll be dealing with a k-flat. Okay, so first we'll solve the system of equations. We're well on our way with this information here. This gives, returning to the system of equations, x1 minus 2x3 equals negative 1, x2 minus x3 equals negative 1, and for completeness, 0 equals 0. Or, if we solve for x1, x2, and x3, as you always do with a system of equations, we get negative 1 plus 2x3, negative 1 plus x3, and x3, well, x3 I guess equals x3. Now, let's introduce a free variable. So we'll let, say, r be the free variable, and then we can express x1, x2, x3 as a free variable. We'll have the general solution to the system of equations. Then we'll check with the definition of k-flat and see what format we need to put the solution in. So let r equal x sub 3 be a free variable. Then the solution becomes, in terms of the free variable, x1 is negative 1 plus 2r, x2 is negative 1 plus r, and x3 is r, where r can be any real number. I tell you what, let's rewrite this as a vector equation. Or, if we let x vector represent the vector with components, x1, x2, x3, just substituting in the stuff with the r's, we can actually rewrite that as a constant vector plus a scalar multiple, looks like, of the vector 2, 1, 1, where r is an arbitrary real number. Okay, so that's the form of the solutions. Let's check with the notes. Now, a k-flat was a translation of a k-dimensional subspace. Here we have one free variable. We'll be dealing with a one-dimensional subspace. Let's scroll down and grab some notation here. The notation we used for this translation of a vector space was we took a translation vector A and added that to a subspace W. We needed a basis for W, and we got our k-flats expressed in the form vector A plus subspace W. So in this case, we'll take, this is the translation vector, and this single vector is a basis for a subspace. Call it W. So we'll let the translation vector be vector A, which has components negative 1, negative 1, 0, and we'll let subspace W be W equals the span of, it's just a single vector, it's one-dimensional subspace, 2, 1, 1. Then, if we have any x that's a solution, x vector, solution to the original system of equations, it's of this form, A and an element of W. So, the K flat, the 1 flat, that contains all solutions of the system of equations is as follows. So, x vector is a solution to the original system of equations if and only if x vector is in the 1 flat. All right, I promise to represent it as A plus W, where A is a vector, the translation vector given here, W is a subspace. How you're going to describe spaces? By giving a basis. This is an easy one because it's one-dimensional. Okay, so vector A is -1, -1, 0. And the subspace is the span of the vector 2, 1, 1. So there's a solution of that system of equations expressed in terms of a 1 flat. You got any geometry behind this? Yeah, it's a one-dimensional subspace of, looks like we're working in 3 dimensions. Vectors here have 3 components. A one-dimensional subspace of a 3-dimensional space is more commonly called a line. But remember, you got to put all them vectors in standard position to get that line interpretation.